at the same time. On the other hand, when one of these signals is low, you know that you have a data on your data bus. So by playing with all these logic combinations, you can define whether you have a data or an address on the signals, and if you're writing or reading, and whether the CPU is accessing your hardware or another piece of hardware. It's very important not to trigger your own hardware if the CPU is accessing another hardware. Now, you have two steps in learning how to access a bus. The first one is writing. The CPU wants to write to another peripheral. That's the easiest part, because the peripheral is never talking to the CPU. It doesn't have to comply with some timing regulations. It just has to listen to whatever the CPU is telling it and trigger whatever signal is asked by the CPU. Reading information from the CPU, so reading information from the outside world, is a little bit more tricky, because if your hardware does not comply with the timing, you will end up with short circuits or bus contentions, so mainly two people talking at the same time on the bus. So writing is the easiest part, and you have various ways of doing this. You can take plans on the internet based for the Game Boy cartridge. You will find Eagle, Gerber files telling you what is the layout of these pins, and you can, if you have access to the right hardware, you can etch one of these boards by yourself. What I did is, when I bought this cartridge from M3, they will sell you for a couple of dollars more what they call the Rumble Pack. The Rumble Pack is possibly the most stupid piece of hardware I've ever seen. It's one of these cartridges that you put here in the slot 2, and it's just got a motor in it. And when you're playing at some games, I don't know which one exactly, this motor starts rotating and it makes you feel like your game console is moving. So it's actually useless as a game, but it's pretty interesting because it gives you a piece of hardware that you will not worry about hacking, because it's so useless as a game that you just take this thing apart and you will throw away the motor which is over here, and this gives you some space. I would say plenty of space as a surface mount component person, but of course that's about 1 centimeter by 2 centimeter. If you're interested, you can have a look at mine. And this gives you some space to put your own components. And you have here access to all these signals that I mentioned. The chip select signal is somewhere over, I can't remember where chip select is. The data bus is all these pins here are the data bus. The address bus, actually, we don't really care about. You'll see later why. And you have the interrupt signal. So in this parallel bus, again, as a reminder, these address buses tell you which peripheral you're accessing on your cartridge. The data bus tells you what you want to tell your peripherals, and the control bus tells you whether you are writing or reading data. That's about the hardware part. The piece of hardware that we're going to use is called a latch. Now, for the more software-oriented people, let me remind you what a latch is. A latch is a piece of hardware that will remember the state of its input on its output pin as long as the clock signal stays high. When a pin, which is called the clock signal, transitions from a low to high state, the output memorizes whatever is on the input, and as long as this clock signal does not move, the output stays the same. This means that if I put LED on the output of this latch, whatever is happening on the input will be transferred to the output when the clock signal is moving, and when I stop moving using my own control software, this clock signal, the output is remembered. The state of the input is remembered on the output. So basically, this is your basic hardware for blinking LED. What your software will tell is trigger this clock, write something on the data bus. The processor does whatever it wants. The output stays at the same time as the input when you switch the clock. And when you want to change the state of the LED, just write again on this data bus. Now, how do you write on a data bus? A data bus is a piece of hardware, and we're talking software. Well, you have a mapping between your address space and the pins that are triggered by writing to the address bus. And this is something you cannot invent. It's given by the hardware manufacturer. So what you do is you go on the web, search for NDS hardware memory map, and you will find a list of the memory maps, so the addresses at which you can write to whatever peripherals. So you have an address space for the RAM. You should not write there. It's not a good idea. You have address space for the ROM. You're not allowed to write there. It will not do anything. And you have address space for the cartridge. And when you read on the web the documentations, you will find that the cartridge address space starts at 8 million. So what you do is, by writing on address 8 million, you will write part of this address bus on this address space here, on these address pins, and the value that you have given here, so which I give to my function as an argument, this value will go onto the data bus. Remember, address bus is where you are writing, data bus is what you are writing. And since I am writing to this address, the write signal will be triggered, as opposed if I were to reading, as will be seen later. So when I write this piece of code here in C, I will trigger my address bus with this address, my data bus with this value, and trigger the write signal. And my logic here is cabled so that I only trigger my latch when the write signal goes low, and my data bus will be copied onto the output. So this is the basic way of accessing hardware. And this is something that you're not allowed to do on a usual Linux box, because doing this on a Linux box will make you reach an address space that you're not allowed to. Only the kernel is allowed to access any address space. The user is only allowed to access a finite amount of memory, or defined by the kernel. And this will lead to a segmentation fault. Segmentation fault simply means that you are accessing a memory segment that you're not allowed to access. UC Linux doesn't care because it doesn't have a memory management unit. So UC Linux can access any kind of space. So as a user, I'm allowed to reach this kind of address space. So this kind of writing is something you're only allowed on MMU-less systems or in the kernel of a usual Linux box with a memory management unit. So the thing that people are usually not familiar with is this kind of writing, which tells you this address space is considered as a pointer towards 16-bit. You tell the size of the memory chunk that you're addressing with this address, and you say the content of this address space is equal to a value. So this is the kind of writing that you will find very often on embedded systems, but is not really familiar to usual C programmers. And this is what happens. So actually, I just broke my LED when I took my NDS out of my bag, so I will not demonstrate the LED part. You have your two LEDs here, which are controlled by the Linux software, which keeps on writing 1 and 0. So the argument that you give and the 0 switches on the LED, switches off the LED. So much for controlling something. So controlling a piece of digital hardware. So in this case, we're only sending 0 or 3 volt. So this means you can control a relay, you can control a stepper motor, you can control binary state of any kind of hardware through the NDS. I told you that I'm interested in knowing what my environment is doing and talking to the environment. So knowing what the environment is doing means reading what analog to digital converter is doing. So an analog to digital converter is a piece of hardware. You give it a voltage, it will generate the bits which represent the voltage, the value of the voltage that it sees on the input. And it's a little bit more tricky because in this case, the processor is accessing all the time its bus. And if your piece of hardware talks to the bus at the same time in the CPU, there's a short circuit and a risk of damaging the hardware. So in this case, you must be very careful to wire correctly all the control signals so that the analog to digital converter only talks on the bus. We say it goes from a high impedance state to a low impedance state. It will only talk on the bus when it's allowed to. And allowed to means read bar going to a low state. And then as an example, I took one of these faster analog devices, analog to digital converter. It's a 12-bit converter. And here is an example of an acquisition that I made through this analog to digital converter using a 4 kilohertz sine wave.